Thank you very much, Alice. Can you guys hear me okay? Is this roughly about right? Okay, great. So obviously, Jeff is very sad that he could not be here. I'm also sad he couldn't be here because I spent most of the day, doing this presentation. The upside is that it let me create this really great joke. At Cloudera, we are all about reliability via redundancy. So it would not have been okay to send but one data scientist to the conference because obviously one data scientist can go down. So we sent 3 data scientists to the conference. So I'm actually not feeling that great myself, and in case I keel over during this talk, my colleague Tom Pierce is in the back there and will be ready to fill in for me in a moment's notice. Thank you, Tom. Okay, so what are we talking about today? This is probably going to be a little bit different than what was in the sort of syllabus or abstract for this talk, because I did it instead of Jeff, and so it's biased towards stuff that I know. But I worked on the ad auction system when I was at Google, and I'm sort of trained as a statistician. And so my area of expertise is really around evaluating machine learning models instead of actually creating them. So I want to talk about a little bit about sort of what I see as the differences between creating and running machine learning models in industry versus in academia. And then I want to talk for quite a while about sort of the current state of machine learning in the Hadoop world and sort of where we think things are headed. And then finally, I have just a bunch of requests, both in terms of like specific applications and then kind of more general abstract theoretical problems that we in industry need academia to solve for us. So it's kind of my opportunity to beg and plead for you guys to work on some of the stuff that will be most helpful to us. Okay? All right, industrial machine learning. Kind of sounds like this should be the name of like a German band or something like that, doesn't it? Anyway, all right. Talking about deltas between industrial and academia versus industry, right? First and foremost, model evaluation is probably the single biggest difference, I want to say. So first and foremost, most of the time in an ad system or in like a social network prediction system, or really honestly in any kind of industrial system, the machine learning component is just one system as part of an overall complex system, right? And these systems are usually so complicated that no one can actually reason about them. There was a time when I was at Google where the ad system started sort of showing fewer ads on a kind of a consistent basis. And there are all these knobs you can use to kind of control roughly how many ads should be shown. So when they turned the knobs to kind of increase the number of ads to be shown, it worked for like a day, and then the number of ads kind of started falling again, right? And people really had no idea what was going on. So they basically spent a few months like trying to understand the system. And I was relatively new to Google at the time, and I asked my mentor, this guy named Daniel Wright, Daniel, is it possible that the ad system has become self-aware and that it doesn't like ads? This is like a fairly persistent problem. Second big problem is this is a business, and there are usually multiple objective functions. And there's not really a great way to really assign weights to these objective functions that are consistent on any kind of time frame. So you can think of this in the ad context, you would have like revenue, right? It's sort of a clearly, like revenue, the amount of money I make today. But I also care about click-through rate. And I also care about long-term sort of quality metrics that are basically, essentially if you turn up the ad system, to show lots and lots of ads, you'll make lots of money today, but you'll basically make people blind to ads eventually and then they won't click on them anymore, right? So you kind of have like all these different goals you need to balance over time. And so generally when you're working on a problem, what you aim for is like Pareto optimization or some kind of change that can roughly be tuned between like what your different goals are, if that makes sense. Something that sort of tunes between like money right now and money kind of further on down the line, okay? Just because you don't really know what the business goal is going to be at the time that you actually are ready to launch your system. All right. Predictive accuracy is only useful up to a point. You want to have good models. You want them to be predictive. But sometimes increasing predictive accuracy can actually harm other objectives you have. And sort of the two cases for this that I know about, like reasonably familiar with, are obviously computational advertising and then friend recommendations in social networks. So computational advertising, it's often the case that a like objectively better machine learning model will make you less money, just for any number of reasons. Again, it's a function of being part of a complex system. And if you just change the machine learning component without really anticipating how advertisers will change their bids or how this will affect budgets or anything like that, you can end up making less money overall. This is like generally not a good thing, right? Friend recommendations. So LinkedIn, Facebook, they all do friend recommendations. And this is a huge source of growth in their social networks. It's something like 40% of all new edges in either the LinkedIn or the Facebook social graph are driven by these systems. But they're also products in the social network. And as products in the social network, their goal is to get you to spend more time in the social network. So for instance, I'm almost sure, although I don't know anyone who can confirm this, that Facebook has like a attractive girl sort of friend recommendation model that they like mix in with my regular friend recommendations. Like these are just like friends of my friends who are very, very nice to look at, and they just throw them in there every now and again. I'm sure it's like the same thing for females and all that kind of stuff, right? Just to get me to spend more time looking at friend recommendations. I guarantee they do this. It would be like crazy if they didn't. Anyway. Okay. All right. So other big delta, systems precede algorithms. It is essentially never the case that you get to start from a blackboard where you write down a set of equations that has some great properties, and then you design a system that implements those set of equations to solve some machine learning problem. That basically never happens, right? So what you have instead is sort of the existing computational infrastructure at whatever company you're working at. And this computational infrastructure has a number of aspects to it. One, it's very general purpose. It's designed to be used for lots of things. It's pretty cheap. The number of like GPU units that are available to industry is like relatively limited in most fields. And the other big thing is that it's shared. This is running reporting stuff. This might be running production serving systems. There's a lot of activity on these systems that's not just machine learning. These machines are generally not yours in any kind of real sense. Okay. And so these are all real constraints on the kinds of machine learning models you can develop. But what I'd like to argue, and at least what I'd like you to think about, first of all, I'd like you to think very seriously about choosing industry over academia. I would encourage that to basically anybody. It's so much fun, really, like not for nothing. And two is that these constraints drive innovation. Like Michelangelo, when he was constructing the David is like was constructed from a very terrible piece of marble. It was like way, way, way too thin, right? Michelangelo had a big problem actually finishing things, and he needed constraints that were like sort of severe enough to make him actually finish something. And in this case, a terrible piece of marble was key to that. And some of the things that I love best in machine learning, at least recently, come from system-based constraints. Valpo-Wabbit has this hashing trick they do, right? Where you sort of like basically allow collisions between hashing features, and you do this so you can fit more features in memory. That's like sort of the ostensible purpose for doing this. But it turns out to have these really nice regularization properties, right? SETI at Google, sort of the original ad system at Google, both these things were really, they started with systems. They started with systems that they knew that could do certain things, and then they developed machine learning algorithms that could fit and work with the constraints of those systems. And they've worked out, you know, staggeringly well, really, over the last 10 years or so. Okay. All right, other big delta is around the workflow. So this I lifted from the Practice Over Theory blog, and so if that blogger is out there, I thank him very much for letting me borrow this. This is just a really basic supervised learning workflow. It's kind of the way you would think about things. We have raw data, we do some preparation on the data, we create a training set, a validation set, we build a model, we do some validation, we kind of loop in that process, make our model better and better, and then we apply this model to new data and we make a lot of money, right? Sounds fantastic, okay. That's not really the way things actually kind of tend to work, you know, in industry. At least the size of those boxes isn't quite right. If I wanted the size of those boxes to represent the amount of time you spend doing each of these different steps, the sizing would be like completely inappropriate, right? Okay, so first of all, what we really want to do is optimize like the overall process. A lot of stuff I see is focused on optimizing model fitting. Model fitting is very, very important. We want to have fast model fitting, but we really want to have fast everything. We want to have fast feature extraction. We want to have fast validation. We want to have fast evaluation. We want to parallelize everything we can so we can basically train and evaluate as many models as possible because that's how we learn things, okay? A lot of the times, sort of the difference between like a logistic regression model and an SVM model is really kind of a round-off error compared to the difference you get from adding better features or new data to your model. So basically, if it's a lot easier for you to deploy a logistic regression model because you have a logistic regression model in production already, you're probably better off iterating on features instead of trying to swap that out with an SVM model that uses exactly the same features. It's not always true. I'm just saying it's a good rule of thumb, okay? You want fast model deployment. So these models are running in production, so they have to basically be able to extract features from production data as well as like offline data, right? So what you really want to have is kind of a common sort of DSL for specifying how to let you just define features, and we'll generate code for you that will work in both your kind of training phase and your serving phase. You also want the output of your model to be servable. You don't want to spend any time coding, like the implementation of this like a logistic regression model, right? You just want to like, file comes out, boom, plug it into serving, off you go, all right? And then finally, in web stuff, a lot of times, the only validation you do is just sanity checking, right? Just make sure the results aren't crazy. What you want to do is get the numbers out there, like get the models out there as fast as possible, get them on a really small sample of data, learn what you can from that, and then kind of iterate and keep going. All right. That's my little diatribe. Just keep all that stuff in mind. Please come to industry. We desperately need you. All right. So Hadoop is where the data is. I'll talk a little bit about, I'm going to assume most of you are basically familiar with Hadoop. I'm just going to kind of quickly go over the sort of the infrastructure, the platform, all that good stuff, and then we'll get on to the fun stuff. So Hadoop is this whole platform for managing data, right? Kind of every step of the way. You start with commodity servers, you start with a commodity operating system, you start with open source tools for handling configuration, and then doing like sort of coordination across services, all this good stuff, all right? You have a number of different options for storing your data. So first and foremost, obviously we start with distributed schemaless storage, HDFS. There's also Ceph. If you guys haven't seen Ceph, and I'm assuming I'm pronouncing that correctly, that's definitely worth checking out as sort of an alternative distributed file system that can be plugged into HDFS and be used as part of Hadoop. I'm sort of biased here in my sort of choices. I totally knew that was going to happen. It was like literally but a matter of time. All right. I'm biased in my selection of append-only storage formats, right? But what I love Avro as a storage format. I love RC files, which is a storage format used in Hive. That's really, it's columnar storage and very, very fast to query. And then HCatalog, which is this sort of generalization of the Hive metastore so that you can use it across Pig, any kind of other different MapReduce job, right? And then finally, more and more important all the time, HBase for mutable key value storage. Okay. The other sort of great thing about Hadoop is how much work is being done right now around integrating it with other things. So Fuse is like an NFS, basically, interface for Hadoop. Fairly fantastic to use. Like you just sort of, theoretically speaking, copy files into HDFS, drag them in, drag them out. Works with lots of other tools. JDBC and ODBC drivers for Hive are kind of fantastic. And then we have Flume for sort of moving massive amounts of log data or sensor data or really any kind of data you can think of into HDFS. And then Scoop for pulling data in from relational databases, but probably more commonly writing out data to relational databases. All right. So we have this whole wonderful ecosystem already that just takes care of a lot of the boilerplate stuff that you really don't want to have to worry about, right? Okay. So current state of the world, machine learning and Hadoop. All right. So if we think of machine learning as this kind of like data preparation phase and this model fitting phase and this kind of model evaluation phase, Hadoop is pretty fantastic for the data preparation phase. In particular, I should say MapReduce is pretty fantastic for the data preparation phase and for the evaluation phase. For the model fitting phase, it really kind of depends on what you're doing. There are a lot of times there are like options where MapReduce is going to be really slow. And you use it if you have to, or it's easy, or it's convenient. But if you could choose something else, you kind of might like to really seriously consider that. It's kind of a wishy-washy statement. You really want to consider that, I guess is my thought. All right. So certain kinds of model fitting problems are like a pretty good fit for MapReduce, and this is just in terms of like what we see in industry. So recommendation systems. Recommendation systems like any kind of product recommendation, friend recommendation, anything like that is a great fit for MapReduce. And then we've seen all these sort of other models that are based on decision trees. So there's Planet, which was done by some colleagues of mine at Google. And there's gradient boosted decision trees, which is a Yahoo sort of like model of this, right? The idea here is we're just running big MapReduce jobs that are looking at sort of input splits. If they're too big to fit in memory, it kind of does a MapReduce job over them to figure out where the next split should be. And if they can fit in memory, it just loads the data in memory and processes it there. Even in the case of these, though, like for the gradient boosted decision trees, if you look at this paper, the Yahoo guys did an MPI-based implementation of this that's like 6 times faster than the MapReduce implementation, right? MapReduce obviously is always going to be a batch model, right? So you're never going to use it for sort of any kind of online learning system. I mean, basically the biggest sort of decision point I think with MapReduce for machine learning is latency. Recommendation systems usually only need to be updated like once a day, right? You have 24 hours to get your model done. That's, you know, plenty of time, right? They're going to let you just do any, you know, any number of map reduces, basically, right? There is just unbelievable amounts of detail on all these different algorithms in the KDD talk from this year. So I'm going to mostly skip over this stuff and talk about other things instead. Okay? All right. Again, sort of back to the point where Hadoop is really useful for things. Data preparation, feature engineering. So this is really the process of taking in some data, whether it's images or log files or whatever, and I want to extract my features from it and then prepare them for input to my machine learning system. So the kind of like obvious tools for this, most people think of would be things like Pig and Hive, but I'd like to sort of dissuade you from using those if at all possible, just because there's sort of this mismatch between the models that Hive and Pig are going to like require you to, like the sort of way you specify feature extraction code in Pig and Hive, and how you might end up doing that in a production system. So what you kind of would have to sort of hack around it by coming up with like maybe some UDFs or something like that. So I mean, ideally, I'm thinking your feature extraction code is in Java. You want to be using the same feature extraction code for the online-offline process to the extent that it's possible. The way to link Java into Hive and Pig is with UDFs. Kind of by the point you're using UDFs, you really don't want to be using UDFs in these languages, like if at all possible. So better off, in my opinion, sticking with Java and Scala and using one of really the very kind of new and exciting like APIs that have been developed for creating big long chains of MapReduce jobs in these higher level languages, right? So Crunch, I'm somewhat biased in favor of since I wrote like a pretty healthy chunk of it. Scooby from the Nikta guys is wonderful, and if you guys get a chance to check it out, I highly recommend it. Cascading has been around for longer than anything else, was kind of the first model like this. The only thing that I kind of like don't like about cascading, this is my personal bias, is that it's sort of a very tuple-oriented model. It basically feels a lot like Pig or Hive, essentially, but it just happens to be in Java. And then Jackal, which is an IBM-specific thing, which is sort of kind of similar to Pig, but operates on like complex records in JSON. So I mean, it's sort of like great if you happen to work at IBM, but I don't think they've open sourced it or anything like that, so I don't know how to get a hold of it. Does anyone know if they've open sourced Jackal? I haven't seen it anywhere. No? No one's seen it? Okay. All right. Let's talk a little bit about Mahout. Mahout is sort of the starting place for people when they come to machine learning. A lot of times our customers are like, I've got a bunch of data, I want to do some data mining on it, right? What they really want is kind of like data mining in a box, or like data mining as a service. And we, of course, who are all experts in these things, know that there's really no such thing as that. There really isn't data mining in a box, at least right now, insofar as I can tell. General nodding in the audience. Okay, good to hear. All right. Okay, so almost always you're doing some kind of custom tweaks or modifications to whatever algorithms you come up with, all right? Mahout right now is a very disparate collection of algorithms, and I mean that in the most general sense possible. It's disparate in the terms of they do different things. It's disparate in terms of how long the implementations have been around, how battle-tested they are, how strongly I would recommend you use them. But sort of they roughly fall into four main classes. There's a big recommendation system, there's clustering algorithms, classification algorithms, and a frequent item set mining algorithm, kind of roughly a priori, if you're familiar with a priori, right? These are all sort of like independent libraries in a real sense. There's not a ton of code sharing across these, and it's not, you can't just like really sort of like swap a lot of different implementations as much as you might like to, okay? So a little bit of an opinion on these things. Far and away, I think the best library in Mahout is the taste recommendation system. So it's like cf.taste is the Javadoc API. And that's really just a function of, it's been around the longest, it's been battle tested, people have been hammering this thing for a couple of years now, so it's in pretty good shape. It's very widely deployed. If you look at like the list of like powered by projects on the Mahout website, recommendation systems kind of tend to dominate. Foursquare did a really good blog post on sort of their use of taste and like sort of their own modifications to it. Recently, the sort of SVD, the singular value decomposition algorithms there have gotten a lot of work and have become like quite a bit better. Good libraries, the online stochastic gradient descent algorithm is actually pretty good. It doesn't actually use MapReduce at all. It's a totally online algorithm. That said, I kind of think that Valpa-Wabbit with AllReduce has sort of lapped it in the past few months or so. Just like my personal opinion, basically. Things you should probably not use. Naive Bayes. The Naive Bayes implementation is like super simple. Naive Bayes is super simple, right? If you're going to use Naive Bayes, just write Naive Bayes. Like, don't bother using the Mahout-based implementation. It's just, it's not really worth your time. There's a bunch of limitations with it. I don't recommend it. Okay, so sort of the challenges around Mahout as an open source project. I mentioned there's lots of tweaks and lots of custom modifications to things. And I call this the secret sauce effect. Like, no one wants to talk about their machine learning implementation. No industry wants to talk about it because everybody does something slightly differently, and everybody thinks the slightly different thing they do is like the magic that makes everything work and is like totally wonderful. And I don't believe this for a second. Everybody's basically doing online stochastic gradient descent. You know what I mean? The differences in your rates, I really don't care, like all that kind of stuff. But look, whatever. No one talks about this stuff, right? And in particular, no one contributes it back to Mahout because you've made all these tweaks. They're really optimized for your use case. And so it's not like a generally applicable thing most of the time, right? Okay. There's another thing where, I mean, a lot of these algorithms are based on MapReduce. Mahout is pretty strongly associated with MapReduce. And a lot of the cutting edge stuff in machine learning, the stuff I see here at this conference, isn't making use of machine learning, isn't making use of MapReduce. It would be really funny if it wasn't making use of machine learning. I love the non-parametric Bayes stuff, I really do. Anyway, so this is big delta, right? So it's not obvious how some graduate student can take a project they've worked on and incorporate it directly into Mahout and make it like widely available for everyone to use. It's just a lot of work and a lot of hassle and a lot of overhead for not really very much payoff. And this is a problem. I don't have a solution to this. I'm just sort of pointing this out as a problem. Okay. I'm sadly going to blow through these, and I feel bad about this because I love a couple of these projects. There are lots of like currently available sort of extensions to MapReduce that like are really great for machine learning. SystemML from IBM is kind of like a crunch or pig for working with matrices, which is kind of cool. AllReduce, I'm just a huge fan of. This is the thing out of like John Langford's group at Yahoo Research. A few other people actually, I think I saw a poster for it out in the hallway. This basically adds a broadcast step to the very end of the like MapReduce kind of computation. Speeds up a huge amount of like very common machine learning tasks. Like the performance numbers they're showing are fantastic. No MapReduce at all. You guys just heard about Spark, so I won't like harp on that too much. But I'm a huge fan of Spark as well. I pretty much learned Scala by copying much of Spark's code. And then there are a number of R-based systems, which I'm also a huge fan of. My favorite one of these is probably Ricardo at IBM, which gets much less play than the other three. But it really embraces this idea of letting Hadoop do all the things that Hadoop is really great at, which is like aggregating things, counting things, distributing things, all that good stuff, and then doing kind of the hardcore optimization logic inside of R itself. And it's a really very smooth interface between like the data stored in the HDFS cluster and then pulling the data back into R, doing some computation, and then sort of running the next step. So it would be something that would be like fantastic for IBM to open source. If anyone from here is from IBM, not going to admit it, okay, that's fine, doesn't matter. All right. All right, machine learning in Hadoop, where we're going next. Okay. This is actually, I got this from the Uncyclopedia. This is the, have you guys ever seen the Uncyclopedia? It's like a much less useful version of Wikipedia. But sort of this is the image they have for the Cambrian explosion. And that's kind of where I think we're going with Hadoop right now. Cambrian explosion, yes, is where most of the phyla that came into existence occurred in like 530 million years. It was just huge blossoming of diversity in creatures and animals and basically everything, right? And sort of the impetus for this Cambrian explosion is sort of MRV2 and Yarn, okay? So right now, sort of one of the big problems with the Hadoop cluster is the only thing you can really run on it, the only type of job you can run on it is a MapReduce. And there's this big honking server called the job tracker that keeps track of everything, does all the resource allocation, does all the job scheduling, keeps track of all the tasks. And it's basically the bottleneck in Hadoop clusters right now. You can only scale a cluster up to about 4,000 nodes right now because of this thing. Essentially, it needs to keep all this data in memory, okay? So MRV2, they basically sort of took this thing apart, rewrote the whole system from scratch. It's a little scary, but we're testing it very, very thoroughly, I promise. They basically split up resource management and job scheduling and the process of actually managing the tasks for each individual job into completely separate servers. So this is going to kind of bump the sort of size that you can basically, you can have like up to 10,000 nodes or so in a Hadoop cluster, right? Which is kind of fantastic for scalability purposes. But it's even better because now MapReduce is basically like a user land library. So you can specify any kind of application you want to run in Hadoop just by interacting with these MRV2 APIs. I should say the Yarn APIs in particular. And there are a lot of projects already that are basically working on integrating with Yarn. There's one called Hamster, which will be MPI on Hadoop. We'll be able to do sort of native BSP. So right now Giraffe, if you guys are familiar with Giraffe, it's a bulk synchronous parallel kind of engine. It's basically a hack on top of a map-only job in MapReduce. We'll be able to do this natively going forward. Spark, Matthias already actually has a Spark Yarn project out on GitHub, so you can actually like I'm not sure if it works. Is Matai here? Does it actually work, Matai? Is he not here? Okay. Somebody ask Matai when you see him, does it actually work? I haven't actually checked. And then I've seen, talk at least between the Allreduce guys and Joseph and the GraphLab guys about doing something where they will have their systems run on Yarn as well. And this is just absolutely fantastic. This really, I'm super optimistic. This will close the gap between the cutting edge machine learning algorithms and what is available to industry to work with. Okay. All right. Finishing up, some things, these are my pleas for you. A couple of specific problems and then some more general things, okay? All right. This is something I've been looking into recently because I've had basically 3 different customers come to me with some variant of this same problem. They need to detect basically system anomalies, essentially, on basically essentially time series data. And you can think of this as sensor data. So you might think of this as some industrial, I have to be kind of vaguely generic as to not give away what I'm talking about here, right? But you have some kind of industrial system that needs to be monitored in some way. And it has lots and lots and lots of different components that are all interacting with each other and lots of different sensors that could be measuring things like pressure or, electricity or something else. Sorry, I'm being kind of mysterious. But they come in at very high volume. There are lots of these sensors, and they have a very sort of fine degree of measurement. So we should be thinking kind of anywhere between 100,000 writes per second and 1 million writes per second, like very, very high volume for these things. Positive events is sort of a kind of unfortunate choice of terms, since usually positive event is like really big explosion. That would be a positive event, right? It's time series data, so we have a feature extraction challenge. There are sort of things like SACs, if you guys know much about time series and machine learning. Actually, if anyone knows much about time series and machine learning, please come talk to me after this talk. Things like SACs for basically kind of imposing symbols onto time series data. But there's not a whole lot of work around multivariate time series, where I have all these different sensors, and it's possible that some combination of like sensor readings across different systems adds up to the system's going to explode in 15 minutes. That's kind of the problem we're talking about here. It's not really clear what the right time horizon is. I look at time series algorithms, and usually it's the case that you specify sort of what the time window is going to be that you're going to like consider events over. And I want like the non-parametric Bayes version of this, where I don't have to specify the time window, and I can just say, it's like there's a Chinese restaurant process for the time window, and then you just go off and compute, and I'm happy. That's great. The models have to be relatively compact and simple because there's very tight SLAs on these things. If the system's going to explode in 15 minutes, I have to know that like really basically as soon as possible. And the stakes are really, really high, like billions and billions and billions of dollars in lawsuits. And this isn't an academic problem, guys. This is happening like right now. The companies want to be deploying systems in like 6 months, and I have no idea what to tell them. Oh, we're videotaping this, aren't we? That's too bad. I'm working really hard on figuring out what to tell them. All right. Okay. So anyway, like I said, seriously, if anyone knows about this stuff, like come talk to me. I want to hear all about this stuff. Okay. This is also a request. Really, feature engineering is really, really important. And it's something that I don't feel like gets, like, I guess I feel, Jeff feels, Tom feels, doesn't really get that much attention in the literature. There are so many great problems in feature extraction, right? There's dealing with hierarchical feature representation. There's understanding like what the cost of adding a new feature is to my model, right? All this kind of great stuff that is just sort of massively dispersed across different industries, right? So you guys actually, maybe the best resource from this is from NIPS in 2003. There was a contest to do sort of different feature extraction models. But that's like 8 years ago, guys. I want you to do this like basically every year to the extent that's possible. I always want to be up to date on this stuff. And then, I mean, it's spread out across different disciplines. So like the NLP guys have their own sort of lingo for this. The information retrieval guys have their own lingo for this. It makes it really, really hard for me to Google for stuff, basically. That's what I'm talking about, right? I can't like just go search on a term and find everything that I want to know. There's not like a lingo I can learn and then go like understand everything in the industry, right? This is a really big problem for me. Like no fooling. I would love to have like a really good solution to this. All right. Okay. So, and then kind of finally, this is sort of, I think, along the lines of the themes I've talked about so far, I'd like to have a broader ontology for model selection. So there's just a bunch of stuff I tend to care about above predictive accuracy a lot of the times when I'm making the decision about choosing a model, right? So I want a model that's going to, in particular, satisfy my latency constraints on like how quickly I have to respond with a score in my production system, right? That really puts a very serious limitation on how complex my model is allowed to be, right? Model refresh time is a fairly big thing. Like, it's just a huge difference between my model choice if the data is coming in an online fashion versus like I'm getting the data every 24 hours, and so it's not a huge deal if the model doesn't get refreshed. There's a big difference between like a recommendation system that can be updated every 24 hours, and you know what, if it fails, it's not the end of the world because I have yesterday's recommendation system and the world of movie preferences is not massively changed in a single day, that kind of thing. Versus like an online ad system where it's actually a really big deal to have an online learning system that can be updated like in 15 minutes, anytime some new trend gets picked up or some advertiser like finds a new keyword that's really profitable. Excuse me, you want to get as much competition in there as fast as possible. All right, and then of course, robustness and reliability. The SETI guys talk about this a lot. SETI went through numerous iterations inside of Google. If you guys are familiar with SETI at all, it's like just a great machine learning library. It's used on a very wide range of projects inside of Google. But it went through several iterations, a lot of which required a lot more babysitting, really. Babysitting is kind of like maybe the worst thing you can say about a system inside of Google, I think. Carrying, like machine learning experts carrying pagers. You guys familiar with carrying pagers? Does that mean anything to anybody? Few people, right? Yeah. Carrying pagers is really bad. You don't want to carry a pager. You want the system to be reliable, and you want it to be fairly predictable so that the pager can be handed off to somebody who specializes in carrying pagers for lots and lots of systems, right? You don't want to be the guy getting woken up at 2 in the morning because things fell over, right? That kind of thing. So these are all really very important considerations in model selection that we just don't really kind of fit into our typical sort of way of thinking about how we choose models. Okay. So I think we got I both managed to finish early. Have enough time? I have 5 minutes? Okay. All right, 5 minutes for questions roughly. And if anyone wants a job, we are hiring both data scientists and interns. I know, is it okay to recruit people at this thing? Is it fine? I was cool or not. Yeah, it's fine? Okay. But yeah, any questions? It's quite possible it's a hard question. I'll ask Tom to answer it, since he knows a lot more about the stuff than I do. But yeah. Yes?
So obviously a bunch of the ML algorithms in the pipeline these days are unsupervised and semi-unsupervised. We also talk about supervised learning. So, I mean, are people in the implementation not thinking about unsupervised learning, or is that still considered too far ahead?
Oh, like clustering algorithms and that kind of thing? Is that what you mean?
Or also these newer kind of neural network algorithms where you just stick them on giant data for days and weeks, and kind of learn stuff from without features. Without labels.
I am not super familiar with it. Tom, do you have an answer to that?
I don't think there's a whole lot of open source support for that right now, which I guess what we're most interested in. Anywhere that might be happening, it's happening sort of in a closed way in the industry somewhere.
Yeah. So I mean, it's not something I've come across very much.
Yeah. As I understand it, there's sort of a trade-off between serialization and deserialization, and versus network traffic for sending big objects versus small objects.
Yeah.
And so I find myself a lot of time in this problem of I have a matrix and I want to send vectors to different reducers. Do you have anything to say about should I be sending big objects or small objects or pairs versus stripes as I
across the MapReduce?
Yeah.
I mean, it just is going to kind of depend on the structure of your data, right? You want pairs for sparse data and you want stripes for dense data. Is that too simple of an answer?
No, I think that's good. Can we generalize?
That's generally my rule of thumb. Tom?
I agree with that.
You didn't hear it or what? You're good with that? Are you good with that?
Yes.
Okay. Yeah, Tom's good with that. What else? Yeah.
Any open source project you are aware of for DSL languages for the feature extraction?
Man, no, I wish there really was one. Tom, how's that coming?
I'll get on that.
It's very, very much a priority for us, absolutely. Yeah, it's just such an important problem, and it doesn't really get nearly the attention it deserves. So yeah, hopefully we will have something soon. Yeah. Should I ask other people questions? Everyone else? All right. Yeah, go ahead.
So the Hoot API seems to keep changing. Is that a...
Which part? The MapReduce API? The MapReduce API or which?
Yeah, like, so like I bought the Tom White book.
Yeah.
And now that's like completely obsolete.
It's not complete.
Well, not completely obsolete. But it's completely changed. Are we at a point now where that's kind of stable?
I would like to think so. But honestly, I mean, so when they did MRV2, they kept like 90% of the MapReduce APIs the same, which is good. So maybe in this case, the MRV2 stuff, you have to learn the Yarn APIs, which are primarily sort of a set of RPCs for communicating with the resource manager and the scheduler and understanding how the client needs to talk to the application master. So there's maybe more APIs to learn, but at least they have the advantage of not being new APIs. So that mean, to be fair, they'll probably change a little bit too over time, such as life in an open source project. Right? Yes?
So you mentioned the Cambrian explosion, and we know a lot of extensions occur after that. Can you comment about what you think will happen?
Well, I mean, I think that's a great thing. It's a totally fair point. I mean, MapReduce is pretty well established as kind of a common way of doing things. MPI has a lot of backers. I mean, obviously, there's a lot of legacy code that's written in MPI. So if you make things that work well in MPI, a lot of legacy code will just kind of get carried over, roughly. I mean, beyond that, I think it's kind of up to you guys, in a way. I mean, GraphLab is like a pretty solid substrate for developing machine learning algorithms. Spark is a pretty solid substrate for developing machine learning algorithms. I mean, what, GraphLab is going to be in C++ for the foreseeable future? Maybe, not sure about that. I mean, Spark's going to be in Scala. But I mean, it seems to me like the substrates that will be successful are the ones that have machine learning people, i.e. all of you, developing applications that run on top of it. And the ones that don't will roughly die off. So that's a fair answer. Okay. Yes?
And we have an opinion about Storm by Nathan Mars.
So I have not looked at Storm in depth. There was a system like that at Google. I mean, there still is a system like that at Google. I've been gone from Google for like 6 months, so I don't know the state of it right now. The understanding of these streaming systems is that they are usually very tightly coupled to the storage system that you use for kind of maintaining the state of the nodes. In Google, obviously, that's Bigtable. My understanding of the Storm APIs, at least nominally, is that it's supposed to be independent. You can use Cassandra or HBase or anything you want. I find that a little hard to believe. I would almost certainly assume there are some that are like better, like some source systems that it's optimized for, like i.e. whatever one the Backtide guys use it with. These systems also tend to require a lot of babysitting, at least in my experience. So I think online processing is kind of fantastic for a lot of machine learning problems, but I would probably start with Valpo Wabbit. I mean, just to be honest with you, if I was really doing an online machine learning problem. In a lot of other cases, I sort of think incremental processing can like handle a lot of like the dashboarding kind of updating systems. This is my personal opinion. And that's just sort of based on Google experience. Nathan's a really smart guy, and I would not want to discount him. Like, if anybody could figure out like a way to do this that was like really reliable and you didn't have to watch it all the time, it's going to be him. Yes?
Do you have any comments on what you gain from using the wider Hadoop ecosystem as opposed to just the kind of HDFS and MapReduce? And further, what you're likely to lose should you pick the wrong part of the ecosystem that dies out because people love the other one more and you've got a lot of investment into it and you miss a bunch of dead code lying around that we work with.
Okay, so I mean, the first question I heard was why like prefer the like sort of broad, why use tools from the broader Hadoop ecosystem?
Well, not why you use them, but how much you gain on top of it. Say you're trying to persuade sysadmin that you're not going to ruin their cloud by installing more stuff on there.
I guess I'm not sure. I mean, generally the projects that have been picked up in the ecosystem are things that lots of people have found useful, I guess, right? Writing MapReduces tends to be somewhat tedious, so we've come up with a number of different ways of letting people not write MapReduces. Right? I think Uzi for job scheduling and sort of like distributed cron that you don't have to run on a single machine is like absolutely fantastic. I mean, data ingestion is pretty much where problems begin and end. You know what I mean? Like getting the data into the cluster in the first place is another great reason to use Hadoop because whatever system you develop doesn't really have to worry about that anymore. You can do all that ingest. That's why things like Spark have HDFS connectors, right? Because that's where the data goes. I don't know if that's much of an answer to your question. Maybe we should talk afterwards.
Yeah, maybe.
Okay.
Okay. So.
Am I done? Okay.
Yes.
All right. Thank you all very much.